Welcome to our video on solving equations by factoring. We're going to have three main objectives with this one. We're going to look at solving a quadratic by factoring. We're going to look at solving a higher degree polynomial by factoring. And then we're going to look at solving an application using a quadratic equation. So it's going to be a lot of practice with quadratic equations. So let's start there. Quadratics are very common. You see them a lot in math classes and physics. They actually occur a lot in the natural world, so that's why we study them so much. A lot of things can be modeled by a quadratic. And so in its most general form, a quadratic is anything of the form ax squared plus bx plus c, where a cannot be 0. You can have a 0 for b or c, but it just changes, the nature of the quadratic. It changes how we factor them and things like that. So normally, to use our standard techniques for a quadratic, all three numbers have to be non-zero, but technically a quadratic can have a 0b and a 0c. It just can't have a 0a, right? So the true kind of definition of a quadratic is it just has to have the x squared piece. As soon as it has that, we technically call it a quadratic. When it has all three pieces, we call it a trinomial. Tri for three, right? A three-pieced polynomial. And then that's when we know we can use our standard ways of solving these quadratics, like the quadratic formula and things like that. Now, technically, the quadratic formula works for no matter if b or c or both are 0, but we also have a technique of factoring kind of by what we normally call guessing and checking, and that doesn't work so well if b and c are gone. We kind of use slightly different techniques. But anyhow, let's look at an example. We know we can factor a quadratic because of the zero factor property. And the zero factor property tells us that if you have two things that multiply together that equal 0, then either one of the things or both of the things equal 0, right? It is impossible for a times b to equal 0 unless both a or b are 0, or at least one of them, right? They can't both be non-zero numbers. It doesn't work that way, at least not in the real numbers. There are imaginary numbers and there are other counting systems where you can have two non-zero things multiply together to equal 0, but not when we're dealing with real numbers, which is what we're dealing with in standard algebra courses. So anytime a times b equals 0, we know either one or both of those factors have to be 0. That's just a rule. And so when we are able to factor something that is set equal to 0, it helps us because then we know either or both of the factors equal 0, and that's what enables us to actually find solutions. So here's one of those quadratic examples I was talking about that's not the standard quadratic because we don't have the c component, right? C equals 0. We're just left with a equals 3 and b equals 6. And when that happens, you could use the quadratic formula if you have that memorized and you want to use it. But you could also go, hey, I can go back to my simple rules of always try and factor out what they have in common. They both have an x in common, and they're both divisible by 3. So I can factor a 3x out and see what's left over. 3x times x and 3x times 2. So it factors very simply as these two things, and then we know each of the factors, we set them equal to 0, so either 3x equals 0, which means x equals 0, because I divided both sides by 3, or it tells me x plus 2 equals 0, and then I subtract 2 from both sides, and I get x equals negative 2. Then you can plug both of those things into the original equation and verify that they both work, right? If x equals 0, everything goes away. If x equals negative 2, negative 2 squared is 4. 4 times 3 is 12. And then 6 times negative 2 is negative 12. So you get 12 plus negative 12, which in fact is 0. Right, so you see it's much easier when we don't have all three of those pieces. So there are cases where you'll have many equations that don't actually look like they're quadratic, but they can be put into the quadratic form and then solved by factoring. So you always want to keep an eye out for things that are quadratic in form and things that can be manipulated to then be quadratic in form, because solving quadratics become very easy once you know either the quadratic formula or you've practiced being able to kind of guess and check and factor them out, by hand, then you're able to tackle a lot of things once you can see that they're all just quadratics in disguise. Okay, how about a higher degree polynomial? So there are a lot of polynomials out there with degrees that are greater than 2. So we can't always use the tools for factoring quadratics, although often we can, because even when we have things that are higher degree, often with a little manipulation, what we're left with is a quadratic. And here is a standard example of that. First thing we always try to remember is factor out a greatest common factor. You look at everything and go, oh, they all have an x in them. This one's got a 2, this one's got a 2, oh, but that one doesn't. So I can't take a 2x out, but I can take an x out. So let's factor an x out of everything, and we're left with 6x squared minus x minus 2. And you go, oh, look at what we're left with, a quadratic. So then we can factor that quadratic by the guess and check rule, right? We know that it's going to factor to two um, sets of parentheses. It's going to be some amount of x, right, and two constants. The two constants have to multiply to be -2. The two x pieces have to multiply to be 6x squared, right? So -2 can only be a 2 and a 1 or a -2 and a positive 1. So you know these numbers have to be 2 and 1. There's really nothing else they could be. The 6x squared could have been 6x and x, or 3x and 2x, and then of course in either direction. So you could have the 6x over here and the 1x there. You could have the 3x here and the 2x here. And then it's just a matter of checking to see which combination of all of those gives you the -1x in the middle. And when you have the -2 here, you get -4, right? Because -2 times 2. And then on the outside, you get 3 times 1, which is 3. So -4 plus 3 gives me -1, and ta-da, that's how it factors. You also could have just used the quadratic formula and got the two factors that way, but the problem with that is it's going to give you a fraction here. And that thing's going to solve out and give you -2/3. And then you have to know how to manipulate that to make it look better. So you really want to try and practice this factoring technique. It's really helpful. Okay, so once you factor it, you can solve each of those pieces. Remember, we had three pieces. We had the x piece, the 3x minus 2, and the 2x plus 1. So the x piece gives us 0. You solve this. There's that 2/3 I was talking about that you would have got from the quadratic, and the -1/2. So if your goal was to just solve it, right, just find the solutions, using the quadratic formula is fine. But if your goal was to factor it and know what the factors are, then the quadratic formula is a little clunky. You would have gotten those two solutions of -1/2 and 2/3, but then that tells you, right, if these are my zeros, so let's say we were working backwards and we got this out of the quadratic, all we know then is that we'll have x minus 2/3 as one factor, right? And x plus 1/2. Because the rule is it's always x minus the number, right? So x minus 2/3 and then x minus a minus half gives you x plus a half. That is how you get factors, right, from zeros. Zeros meaning, the solutions that you would get out of the quadratic formula. Well, yes, if you put the x in front of it, this is, going to give you the same zeros as the previous three pieces, right? But it's not the same quadratic. When you multiply it all together, your leading coefficient is going to be x, right? X times x times x. It's just x cubed. And our leading coefficient was supposed to be a 6. So what that tells us is we have to kind of augment these things. Instead of x minus 2/3, think about multiplying both sides by 3 and getting 3x minus 2 to get rid of that fraction. And then now you get that. Same thing with instead of x plus 1/2, think about multiplying both things by 2 and getting 2x plus 1. There's that piece. And then now when you use those as factors and slap the x in front, then you get the 6x cubed that you needed to get for your original um, polynomial. But the bottom line is, if you only needed zeros, if you only needed solutions, then go ahead and just use the quadratic formula. All right, our last one is to look at an application that is quadratic, and these come up a lot, right? So here's a typical thing where they tell us the width of a truss is 3 times its height. The area of the triangle is 96 square feet, and they want us to find the width and the height. So if this is 3 times its height, we set the height to be x, therefore the width is 3x. We know the area is 96, and so from that, we come up with the formula. Area is 1/2 base times height. They told us the area was 96, the base was 3x, the height was x, so we plug in everything we know, and then we can solve it because all we have is one unknown, right? So we have, from our previous slide, 96 equals 1/2, right? 3x squared. So how did we get to here? Well, we just multiplied both sides by 2 to get rid of that half, right? Because we don't like having halves. And then 3x times x, we're left with 3x squared. So there's the 192 equals 3x squared, because that is just 96 times 2. Okay, well now we can divide both sides by 3, which gives us 64 equals x squared. Now we could do this and turn it into a quadratic and factor it, but once you have this, isn't it just easier to take the square root of both sides? Because we know the square root of 64 is 8. You just have to remember that when you have x squared and you take the square root, the solution is always plus or minus. So that's where you get plus or minus 8. Or you could go this route and then go, hey, that's a difference of squares, and I know a difference of squares is always the square root plus, right? The square root minus, so it's x plus 8 and x minus 8, and then we get the two solutions of -8 and 8. Now, obviously, we can't have a distance of -8, right? It can't be a height of -8. So we kind of throw that one out and say we know the actual lengths have to be 8, and then the other one is 3 times 8, which is 24. So the one thing you have to remember when you're dealing with word problems, that when they're set in the context of the real world, negative numbers don't normally exist in the real world. So you have to double check that the answers you get make sense in the context of the question. And negatives wouldn't make sense here. So that's why we throw that one away. And instead we say the answers are simply just 3 and 24. And then of course, sorry, 8 and 24. And then you can throw those two in and double check and see that you do in fact get an area of 96. Okay, so to summarize, most things are quadratic, right? We see them a lot, so make sure you're very comfortable with solving a quadratic. Things that are higher degrees than quadratics, you still want to tackle with our basic set of rules of factor out the greatest common factor, and then look at what you have left and reapply the rules to what you have left. Hopefully what you have left is a quadratic, or a difference of squares, a difference of cubes, or a sum of cubes, nice simple things that are easy to factor. And then always keep in mind that there are things that are quadratic in form, right? So you always want to be looking for things like, we've seen these examples, 16x to the fourth plus 3x squared minus 7. That's actually a quadratic in disguise, because instead of x squared x, and nothing, they just, this is now my linear term and this is my squared term, because this is just that thing squared. So keep in mind that anything of the form a box squared plus b box plus c. So anytime you have a term that has something that is the square of the other piece, right? And this is the square of this, then it's quadratic in form. And you can still use the quadratic formula, you can still factor it, you can do all those types of things. The only thing that changes is when you get the solutions for that thingy, the answers aren't going to be what x are, they're going to be what x squared is, right? So let's say your answers were, 4 and 1. Well, that doesn't mean x equals 4 and x equals 1. It means x squared equals 4 and x squared equals 1. Basically, you're finding the solution for what's in the box, right? The b here is just 3, right? A is just 16. And then in the box is x squared. So if you use the quadratic formula or you factor it, the solutions you get are 4x squared. So you'd say, 4 equals x squared, which means x equals plus and minus 2. And then 1 equals x squared, which means x equals plus and minus 1. And you actually end up getting 4 solutions, right? So that's a little bit more advanced. You might not see that for a while, but I want you to keep in mind that you can get things that are quadratic in form that have higher powers than just a square. All right, so keep practicing those quadratics. They come up all the time.